This is all from this paper. It should be fairly evident why I've chosen to talk about this here. It is the paper that gives me a Colburn number of 1, so thank you, Charlie. I'm also highly indebted to the third author here, who's Daniel, who's at this conference, because not only did he write the paper, but he also wrote the talk. I've stolen his slides. As a starting point, anyway. I have changed some of them, but all of the pictures, all of the pretty pictures you see are his. Any mistakes that you see will be mine. So, yes, thank you, Daniel, for at least the starting point of the slide. So, I'm not going to assume any prior knowledge, but I'm assuming most people in the room will have seen a Steiner triple system, STSV, so collection of triples that have the property that every pair is in exactly one of the triples. If you like to think about these pictorially, then you get Daniel to draw nice pictures of triples, which are triangles, and you want a decomposition of the complete graph into triangles. That's the graph theoretic interpretation. If you were at Patrick's talk, you would have seen the coding theory interpretation, or you can just think about these as sets, or as hypergraphs, or various other things. So that's what a Steiner triple system is, and also if you're at Patrick's talk, he defined a couple of other things that I need, but I'm not assuming that you were. So a parallel class is a set of triples which partition the point set, so mutually disjoint triples, as large a set as possible. So here's a Steiner triple system of order 9, all with pretty colours, and if I choose those 3 triples, there, and there, they partition the 9 points into 3 triples, so that is a parallel class. Obviously, if that's going to work, then the order of the Steiner triple system has to be 3 mod 6. It's known that Steiner triple systems exist if and only if the order is 1 or 3 mod 6. Pretty much everything I'm talking about today will be 3 mod 6 because I will be dealing with parallel classes and they don't exist in the 1 mod 6. So Patrick also talked about Kirkman triple systems, which are resolvable Steiner triple systems. So if you can decompose all of the triples into parallel classes, that's called a resolution, and the result is called a Kirkman triple system. And classic theory in this area says these exist for all possible orders. So I want to recast the idea of being resolvable in a slightly different way, and that is to think about things in terms of hypergraph terminology. So there's a notion of a chromatic index in a hypergraph. So a hypergraph is just a set of subsets of a point set. So the Steiner triple system is an example of a hypergraph. And you can think about colouring the edges in the hypergraph, or triples in our triple system. You can give each of them a colour, and a proper colouring is one where triples don't get the same colour if they intersect. So you can ask what's the smallest number of colours that you can colour the edges of a hypergraph with in order to give a proper colouring, and that's the notion of the chromatic index. And this is something that hypergraph people think about a lot. And if you think about this in the specific context of a Steiner triple system, then you quickly work out that the smallest number of colours that you can use is b minus 1 on 2, and that you can only use that many if you find a resolution of your Steiner triple system. Because the most efficient way to colour things, if you think about your favourite colour, say your favourite colour is green, the best you can do is to find a parallel class and colour all of those green, because you're never going to get more triples that are green than a parallel class. So the most efficient way is to use one colour for a parallel class, find another parallel class for your next colour, and so on. And if you do that, then you will use b minus 1 and 2 colours. So that's the best you can do in the case 3 mod 6. And I said I wasn't going to talk much about 1 mod 6, but I will just mention, in the 1 mod 6 case, of course, you can't find parallel classes, but you can find things that are close to parallel classes, and the best you can do in terms of number of colours is v plus 1 on 2. So if I talk about m of v, it will be this quantity here, which is the minimum number of colours that you could plausibly use to colour a Steiner triple system. And there's a conjecture from Alex that in fact you always need either this number or not much more. So you might be able to find a colouring that uses M of V or M of V plus 1, or failing that M of V plus 2, but you'll never need more than 2 more colours than the minimum obvious number. Okay, so in this talk I'm going to be talking about this end of the spectrum. So if you're used to thinking about resolutions and Kirkman triple systems, then you're thinking about the smallest number of colours, the minimum number of colours, the things that...
You have to exclude final plane.
I have to exclude the final plane, yes. Sorry, yes. There is an exception here, very small orders. Apologies, Alex, for misquoting your conjecture. These are the resolvable ones. These are the ones which I think of being far from resolvable. Okay, so they're the Israel-Palestine situation in Steiner world, the things that are very far from being resolvable. So we're going to be talking about these as opposed to the things that are resolvable or nearly resolvable. And I'll mention there's a hypergraph theorem. Is much more general than this, but in the specific case applied to Steiner triple system says that for any Steiner triple system, the chromatic index will be asymptotically M of V. Of course, this conjecture is much stronger than they were saying. It's really very close to M of V. Okay, so an obvious way to try and make something that is far from resolvable is to prevent there being any parallel classes. Because if you have no parallel classes at all, then you're certainly not going to be colouring it sort of efficiently. So, is it possible to do that? Well, there's been a bit of work on this, but it seems very hard to build Steiner triple systems that have no parallel classes at all. So there are a couple of small orders, 15 and 21 have been known for a while. There's none of order 3 or 9. There's only one system at each of those and they have parallel classes. Again, there's a conjecture with Alex's name on it that you can actually build Steiner triple systems without any parallel classes for all orders except these couple of trivial small exceptions. And Darren and Daniel have given a construction for an infinite family of Steiner triple systems that have no parallel class. And if you have no parallel class at all, then you are far from resolvable. You have at least chromatic index of min plus 2. But this only covers a relatively sparse part of the spectrum. And what I want to talk about today is a construction that works for all large orders that allows us to build a Steiner triple system with few disjoint parallel classes, not none. So here these results deal with there being no parallel classes. We will construct one that has few parallel classes and that will be few enough that the chromatic index will be at least min plus 2. We don't actually know what the chromatic index is. We never actually found a colouring. It's a pain in the neck to actually write one of those down in general. We believe it will always be min plus 2, but we didn't actually prove that, except computationally for small cases of our construction. So that's the aim. We want to build things that have few parallel classes and hence need lots of colours. Or by lots, it's sort of 2 more than the usual. 2 more than the minimum. Okay, so what's the strategy? So we're going to use arithmetic mod n, where n is 2 less than the order, so n will be 1 mod 6. And so we'll use the non-zero elements of integers modulo n together with 3 special points, each of which will be called 0, but they'll have different colours. Okay, so I have an orange 0, purple 0, and a green 0. So those are my points. And I'm doing this because I want to think of the labels on the points as being weights of the points. So if I have a set of points that will be just the sum of the labels, and I want all of these not to contribute anything, so they'll be weight 0. And notice that the sum of all of the weights of all of the points is 0. So if you add up all of the elements of Zn and these things, you get a total of 0. So sum of all of the points is 0. We're going to construct a Steiner triple system on these points so that most triples have weight 0. And then if you're looking for a parallel class, you're going to be taking mostly triples that weigh 0, and you know that the total of all of your triples has to be 0, and that's going to be seriously constrain what you can do with the triples that have non-zero weight, of which there will be relatively few, and they'll be in very particular arrangement. Okay, so that's the aim, and we'll use this to show that there's very few ways to get disjoint parallel classes. Okay, so here's the construction. We'll just think about the typical points yet so far, not the colored zeros, but the normal points. We're going to put them into triples that have total weight 0. So any pair x and y is obviously going to go with minus x minus y, mod n. So the total weight of the triple is 0. And that works perfectly fine, except in a few special circumstances. So if I try putting x and minus 2x, the third point in there will be x again, and that doesn't give me 3 distinct points. So that pair won't be covered by triples like this. And the other thing that can go wrong is x with minus x, where the third point should be a 0, and the 0 is not in my set to start. So those triples, those pairs are not covered by triples of this form, but everything else is. The unused pairs I can represent as a graph on the points, and my graphs, the components of my graph are either pizzas or hamburgers. Okay, and it will depend. So what happens? What you do is you take edges like this and you chain them together. So you go x minus 2x, 4x minus 8x, etc. That will go around in a cycle. And that cycle will either be the crust of your pizza, or there'll be one bun of the hamburger, and there'll be another one which is the negative image of this. So it depends whether the group generated by minus 2 includes minus 1 or not. If it includes minus 1, then you get this, you get the pizza. If it doesn't include minus 1, then you have this cycle, and then minus 1 times that cycle is the other part of your component. And the orange edges are joining x to minus x, so they're all of these pairs that are not covered. Okay, so the special pairs look like this. They're either pizzas or hamburgers. And all of the orange edges have weight 0 because they're joining x to minus x. So the only pairs here that have non-zero weight are the crust of the pizza and the buns of the hamburger. And even those are special because they're arranged so that the opposite pair, so that pair and that pair, have complementary weights, and likewise this pair and this pair have complementary weights. And it turns out that so these components will all be of even size. If they're 0 mod 4, that's good for us, we'll call them good. If they're 2 mod 4, that's bad for us, so we'll call them bad. So what do we do? If we're lucky and all the components are good, then we color things like this. So we just two-color the crust of the pizza or the buns of the hamburger, and we note that doing this means that inverse weights, which are opposite in the pizza crust or in the hamburgers, get the same color, and that's important, that the edge with the inverse weight is in the same one factor here, and we then add our 3 special zeros, and we join the orange 0 to the orange edges, and the green 0 to the green edges, and so on. And when you do this, the colored triples, we also have the triple just of the three special zeros. And putting all this together, we get our Steiner triple system. Now think about the triples that have non-zero weight. All of the normal triples have zero weight. Also, all of the orange triples have zero weight because of the way we constructed this. So there's only blue triples and green triples that have non-zero weight. And you can't put two of those together and get zero as a result because of the fact that the inverse weights have the same color. So you can't actually put non-zero weights in a parallel class. That means that actually the only parallel class will be the one containing the three special points. Okay, so that's my claim here. So if you're lucky and all your components are good, then there's at most one parallel class. But life is not always that kind, so you need to be able to deal with the bad points, the bad components. And if you get bad components, then you basically just build in as much of what you want to work and then a small imperfection. So here we have two cross edges which we'd like to color orange, but we've colored them red and colored them purple and green. And over here, likewise, two of the cross edges different color, but everything else will be as it was before. And so we get something that's like the good situation, but with a few imperfections. And it still has the property that if you have inverse weights, these non-zero inverse weights, they get the same color. So the argument goes through as before, except that you now get a few extra possibilities. So you could have a parallel class containing the three special, the triple that contains the three special points, but you can also get parallel classes that use these orange edges which have zero weight, or that use those two cross edges which together have zero weight. So you get a few extra possibilities, but you only get a few extra for each component, and so you put all of that together and you work out that the number of parallel classes is at most 3 times the number of bad components plus 1 for this. Okay, and then you do some number theory, because it all breaks down into sort of how these components work out with the group generated by -1 and -2. This is Euler's phi function. You get some number theoretic condition, use some number theoretic estimates for phi and so on, and you work out that in fact so this is 3 times the number of bad components plus 1, and that goes to 0 relative to v. So the number of parallel classes in these things is sublinear in the number of points, which is what we want. And what that means is a few of the small cases don't work because the number theory is not your friend and things haven't kicked in yet. The smallest is, well, actually, there's a couple that don't work here, but we managed to build them other ways. And then there were 4 that we couldn't see how to build. Don't believe these are genuine exceptions, they're just exceptions for our proof. But everything else bigger than 15, we can construct something that has high chromatic index that's far from resolvable. I should note that we don't have the corresponding result for 6k plus 1. So I haven't talked much about it. You can certainly talk about the chromatic index of Steiner triple systems of order 1 mod 6. You can try and find almost parallel classes. You can try and limit the number of those and so on. We don't have techniques for doing that. So we don't have analogous results for that case here. It seems to be a lot harder. And because I can't resist, I'll also mention we don't have the corresponding result for Latin squares either, so you can do the same thing for Latin squares. In that case, a parallel class is a transversal, a resolution is an orthogonal mate, and you can ask for Latin squares that have few disjoint transversals, and the best result we have there is linear, not sublinear. So again, in that context, even though it's quite similar, we can't get a result this strong. Okay, just quickly, we also found another construction which doesn't work for all admissible orders, but does work for this congruence class. So if V happens to be 15 mod 18, and you use the Bose construction, I don't want to go into this too much, but if you know it, you'll know what I mean. If not, you actually build your Steiner triple system in 3 different levels, where the triples go between levels in the pattern that I've indicated, and use a symmetric idempotent Latin square to tell you how to put triples between this pair. You can use another one to say how to put triples between this pair, another one to say how to put triples between this pair, and so you get 3 choices of quasi-group or Latin square in there, and they all work. Doesn't matter what you use, you get a high chromatic index when V is in this congruence class. And so, because you have lots and lots of choices for what to put in there, you actually get bucket loads of high chromatic index Steiner triple systems in this congruence class. Actually, this number here agrees to within the error term of the total number of Steiner triple systems, but don't be confused about that, don't be misled. We conjecture that actually the proportion of Steiner triple systems that have high chromatic index is vanishingly small. That doesn't contradict what I said about this statement. Okay, so there's really a lot of them, but we think there's still vanishingly few compared to the total. Why do we think that? Did a bunch of computations, built things randomly, colored them randomly, always very easy to color with min plus 1, except when you're really small. And you just look at the numbers for when you do have an exhaustive catalogue, almost everything has a min plus 1 color. So we think these things are actually very rare, but they are very rare. There's bucket loads of them, but comparatively rare. And the other thing I should mention is that if you use the same quasi-group for each of these things, you can build Steiner triple systems which are cyclic, so they have a cyclic automorphism on the point set, and yet they still have this high chromatic index. So having a nice cyclic automorphism doesn't save you from having to use lots of colors. So that was our last theorem, and I just wanted to end by saying Charlie and I have had many happy excursions. This is a photo of, so this is my wife Tracy and Charlie's daughter Sarah, a walk that we did near my place in Melbourne, and I hope there's many more such occasions for us to enjoy your company, Charlie, and thanks for the memories. Happy birthday.
Questions for our speaker?
So were you able to test some small order or whatever triple systems whether the chromatic index is actually?
It is, so it's generally pretty easy to find a min plus 2 coloring for these things. So for all of the small ones, I can't remember how far we went, but I did. Do you guys remember? Certainly up to 100, yeah, 100, couple of hundred maybe. They all had min plus 2 colorings.